Let's take a look at what we will learn today. With today's content, you will be able to explain the SCADA system, the features of sensors and signal processing, Korea's SCADA system in water treatment, explain its application to the water sector in the era of the Fourth Industrial Revolution, and the water industry in the future. Shall we start now?
예, 안녕하세요. 한국수자공사 화성권지사 ICT 담당 구동규 차장입니다. 오늘 화성권지사의 스카다 시스템을 비롯하여 계측 기기로부터 RCS, 그리고 네트워크, 그리고 HMI까지 이루어지는 전 과정을 설명드릴 예정이며 최신 기술인 인공지능 기술을 도입하여 정수장의 약품 주입 공정을 어떻게 최적화하여 예측해서 운영을 하는지 교육생 여러분들에게 도움이 되는 강의를 하도록 하겠습니다.
What is a SCADA system? SCADA is an acronym for Supervisory Control and Data Acquisition, and it refers to a system designed to remotely monitor and control industrial facilities and processes in the industrial field. The SCADA system is used for various applications in energy, oil, gas, waterworks, and wastewater, and transportation. The following shows a configuration diagram of a remote monitoring and control system for facilities using groundwater pumping wells. Data is acquired from the field instrument, transmitted in real time to a remote site, central control center, through the TM, TC, and communication modem and stored in a database, and the necessary data is then provided to clients. Looking at the functions of the SCADA system, logging, archiving comes first. In logging and archiving, the original data is compressed to fit into the SCADA system format and then saved. The remote control history, parameters, and period of time are then stored in a log file. Second, the trend function provides the trend display of real-time or historic data in the form of charts, including multiple trends. Third, in access control, the control function is provided in a set range and group, and the user can check the results on the control screen. Fourth, the automation function is to automate field devices and thus provide the user with convenience functions. Fifth, the alarm function causes the system to generate an alarm when a predetermined value is reached for each situation and provides the user with the alarm contents in various forms such as voice, text, and email. Sixth, the report function uses SQL, RTDB, or logs to create reports and makes it possible to automatically generate data stored in DB and provide the user with daily reports in the form of Excel. Next, let's look at the architecture of the SCADA system. The levels of the SCADA system can be classified into the supervisory level consisting of HMI, server and database. Meanwhile, the communication level connecting the SCADA system to the field devices and the device level including the sensors and local system that monitor and control the field devices. Let's take a closer look at the components of the device level. The first component of the device level is a field device. Field devices are largely divided into sensors and mechanics. The sensors are devices to convert physical, chemical, and biological signals into electrical signals. Mechanics refer to mechanical equipment such as pumps, motors, and valves. The second component of the device is TMTC. TMTC is an abbreviation for telemetering and telecontrol. This is a device that integrates, stores, and transmits signals to send local sensors and mechanical equipment to remote sites. Signals can be largely divided into digital and analog signals. Each signal is also then subdivided into input and output signals based on the control system. The digital input signal is a function to monitor the status of field facilities, while the digital output signal is a function to control the field facilities. The analog input is a signal for monitoring data represented as numbers such as temperature, pressure, and flow rate, while the analog output is a signal for remote control using signals such as pressure, flow rate, and water level. The communication level is divided into parts that connect the field device and TMTC. These are then subdivided into hard wiring, input-output terminal block, of the field device and communication ports using serial communication protocols such as RS-232C, 422, 485, and Ethernet. The method of transmitting data to TMTC and Central Operations Center is divided into wired and wireless communication. For wired data communication, a cable is installed to communicate with a cable modem, while LTE and satellites are used to communicate with remote sites for wireless data communication. In order to configure the system of the Central Operations Center, network devices such as a switching hub, router, and gateway are needed to configure the network between the Central Operations Center and remote sites. The switching hub is a network device installed to configure a small system, and the router is a device for sending and receiving data according to the routing table configured between the remote site and the Central Operations Center. Lastly, the gateway is a device used to convert different types of protocols to support interfaces. With respect to the method on how to configure the system using various network devices, various types of topology such as bus, star, ring, and tree are compared and examined to be set in its favor. The following is the configuration of the communication network between a water treatment plant and remote pressurization plant. The water treatment plant operates various remote facilities such as water intake stations, pressurization plants, and branch valves for the central monitoring system operation. As shown in the figure, the data from the field device of the pressurization plant are collected into the RCS, remote control station, and transmitted to the water treatment plant in real time through networking devices, router, CSU model, etc., so as to communicate with each other. Let's move on to the supervisory level. The first component of the supervisory level is the HMI, Human-Machine Interface. The HMI is a means to provide operators with process data on the screen and allows them to change and control the process. The SCADA software enables the supervisory control of remote facilities through a keypad or touch screen. The next is the serve and client connection. The server acquires and manages data through real-time communication with the devices connected to the SCADA system, and the client operates the process with data received from the server. The database stores operational management history and related data. The types of database are divided into single type, server, client type, and web type. The single type is run on one server computer, and the server client type is run with different functions provided by separating the server and client functions. In addition, the web type is provided with functions through Chrome or Internet Explorer, not a closed network. The SCADA system is expected to improve productivity, workplace safety, and quality, speed up the decision-making process, and reduce costs, time, and risks for operation and maintenance. Let's go into details about the benefits of the SCADA system. The SCADA system can improve the operational efficiency and productivity of the water treatment plant based on the process analysis-based operation and enables the high-quality operation of resources, labor force, and plant assets through control-based optimization using the SCADA system. In addition, it is possible to improve safety through the operation process predefined in the SCADA system, and the process data analysis can prevent errors from occurring in the first place. The SCADA system allows integrated control in the control room through real-time data sharing and past data integration. It also enables the efficient management of plant devices and minimizes downloading time through a centralized supervisory control system. Now we will practice on the automation system, PLC, used in the actual water treatment plant and the networking device that enables communication with remote locations. The PLC, Programmable Logic Controller, is an industrial general-purpose controller installed to automate field facilities, and the router is a networking device installed for communication with remote sites. The DSU is a communication device needed for wired communication with remote sites, and wireless transmission refers to a communication device installed for wireless communication with remote sites.
한국수자원공사 화성권 지사의 전체 개통과 스카다 시스템에 대하여 간략하게 설명을 드리겠습니다. 화성권 지사는 도수 송수 개통 관로 약 76km를 운영 관리하고 있으며 정수장은 시설 용량 26만 톤의 정수를 생산하고 있습니다. 화성정수장은 팔당댐으로부터 원수를 치수하여 연장관로 약 17km 구간의 도수개통 관로를 통하여 화성정수장까지 물이 공급되고 있습니다. 화성정수장은 26만 톤의 정수를 생산하여 평택시, 화성시, 송산시에 맑은 물을 공급하는 체계를 갖추고 있습니다. 스카다 시스템의 주요 감시 화면입니다. 운영 근무자분들은 전체 개통에 나와 있는 주요 데이터들을 감시하고 이에 따른 데이터를 확인하여 제어를 하게 됩니다. 참고적으로 8단 개통에서 정수장으로 들어오는 유량과 관련 데이터입니다. 압력은 1.63kg, 원수 유량은 6,544톤이 현재 정수장에 유입되고 있습니다. 이러한 데이터들은 모두 스카다 시스템을 통해서 데이터베이스화가 되고 있고 이 데이터는 본부, 본사까지 데이터가 전송이 되어 일반 직원들이 그 데이터를 활용하여 의사결정을 하는데 활용 가치가 상당히 높습니다. 화성 정수장의 스카다 시스템 구성에 대하여 간략하게 설명드리도록 하겠습니다. 화성 정수장의 스카다 시스템은 스카다 서버, AI 서버 총 16대로 구성이 되어 운영되고 있습니다. 그리고 스카다 시스템의 핵심 요소인 네트워크 장비는 보시는 바와 같이 L3, L2 등 다양한 스위치와 함께 보안 장비를 포함하여 운영을 하고 있습니다.
Let's look at sensors and signal processing. First, sensors. There are several types of level meters that measure the water level in various ways at the waterworks. Among them, a float level gauge is the most commonly used level meter, and its measuring principle is to convert the analog signal of the float sensor's movement into a DC signal to measure the water level. The range is 1% or so the signal can be transmitted through a BCD or analog output. It is used in various processes and has advantages such as being easy to maintain and cheap. However, there is also a problem in that it does not work when freezing in the water. The measuring principle of a differential pressure level gauge is to use the differential pressure between high pressure and low pressure as a detection method. The range can be set at 0 to 15 meters, and the analog output is used for the signal output. It has relatively high accuracy and is a suitable method for measuring water levels in a closed space. The measuring principle of a pressure level meter is to convert the pressure signal of a piezoelectric device into an electromagnetic signal to measure water levels. The range can be set at 0 to 200 meters, and the analog output and digital output are used for signal output. It is possible to measure high water levels, and its installation is possible even on a slope. Meanwhile, sensor contamination may cause data errors. However, it has an advantage in that measurements can be made even when water is frozen. The measuring principle of an ultrasonic level meter is to measure the ultrasonic signal of the height difference between the floor and the top of the facility and convert it into an electromagnetic signal to measure the water level. The range can be set at 0 to 15 meters, and the analog output is used for the signal output. The ultrasonic level meter can measure high water levels and needs sonic receivers and waveguides. Next up is an electromagnetic flow meter. The electromagnetic flow meter uses the principle of Faraday's laws of induction. Next, let's look at Faraday's law. The basic principle of Faraday's law is that a conductor generates a voltage when it passes through a magnetic field. The use of an electromagnetic flow meter began when Faraday attempted to measure the voltage generated in the river across the Earth's magnetic field to measure the flow rate of the River Thames. The electromagnetic flow meter transmits the flow rate without pressure loss, and it can measure the flow of corrosive liquids. It is used in various fields such as water resources management, sewage treatment, plants, and hydroelectric power generation. The ultrasonic flow meter uses penetration, reflection, refraction, and diffraction phenomena of ultrasonic sound waves with frequencies higher than 20 kHz. It is used for cleaning, detecting shoals of fish, non-destructive testing, fluid measurement, water level, temperature and acceleration measurement. It has a piezoelectric element that converts an electric signal into an ultrasonic signal and then converts the converted ultrasonic signal into the electric signal. Now let's move on to signal processing. The RTU is an electronic device using a microprocessor, which interfaces with objects in the physical world to a DCS or SCADA system by transmitting telemetry data to the system. In addition, the RTU monitors and controls the field digital and analog data and transmits RS 232, 485, 422, Ethernet, and analog signals. A digital signal takes values of 0 and 1 as a discrete signal, such as on-off status signal of pumps and valves. The digital input signal represents on-off status of facilities, and it uses DC24V circuits to transfer signals in the form of values 0 for open, 1 for close. Meanwhile, the digital output signal represents the run-stop status of facilities, and it transmits the run or stop signals from the HMI to RTU in order. Analog signals represent continuous physical values such as voltage, current, temperature, pressure, flow rate, or velocity. The analog input signal refers to the temperature, pressure, flow rate, voltage, current, and water level. This signal can be acquired through DC24V, TD, 4 to 20 mA, and AD converter. The analog output signal can be controlled by transmitting setting values for pressure, flow rate, water level from the HMI to RTU. In the process of level signal transform, the 4 to 20 mA signal is acquired from the level meter, and the data is transmitted through the AD converter and processor. In the process of flow signal transformation, the 4 to 20 mA signal is acquired from the flow meter, and the data is transmitted through the AD converter and processor. The analog signal of the pressure sensor is a continuous signal, and the output value is transmitted by converting the 4 to 20 mA analog signal to each pressure range. And the digital signal of a level switch is acquired by converting output at high and low level contacts into a digital signal. Let's have a look at water treatment in Korea. Water plants in Korea are classified into regional, municipal, and villages according to the water supply scale. The SCADA system is divided according to the water supply facilities. Let's examine the groundwater SCADA system first, looking at it by focusing on monitoring for water quality, quantity, and pump conditions. Pump operation and chlorine injections are done automatically in water tank stations. Monitoring items include water quality such as turbidity, pH, residual chlorine, and temperature, quantity such as tank water level and tank outflow, and pump conditions such as on-off status and operation time. The system configuration consists of the communication method, monitoring location, security equipment, and web services. The system maintenance is performed by local governments and heads of villages, respectively. The local government manages 200 to 300 facilities in the city, and the maintenance is outsourced if necessary. On the other hand, the village unit provides support for citizens, performs real-time inspections, and responds to issues. The budget is supported by the local government. The field system consists of sensors, water level, quality and flow rate for measuring on-site water facilities, and TMTC communication equipment for transmission to central control room, remote site. The Central Control Room Center consists of servers and application programs, HMI, DBMS, to monitor and control data transmitted from remote sites in real time. The single SCADA system is a small-scale system in which an operator monitors and controls the necessary processes, and the RCS is used to automate facilities in local areas since the scope is wide. In addition, the RCS is an automation equipment using programmed algorithms to control field devices for each process, and an individual RCS is incorporated into the SCADA system for configuration. The system configuration is as follows. The field equipment is transmitted to the RCS according to the plane program, and remote monitoring and control are performed using the central system. The maintenance organization is composed of customer support, facility management, operations, and checkup repair to achieve efficient operation and management. Looking at the roles of each organization, the business management team deals with general business affairs, such as finance and human resources management, education, quantity distribution, and customer management. The facility management team performs facility construction and replacement, water supply management and risk management, and the operation team performs the overall water treatment process and manages a 24-hour shift work for tap water production. Lastly, the maintenance team performs facility maintenance and outsourcing management. The SCADA system can be divided into Central System, RCS, and TMTC. The central system consists of a big board capable of integrated monitoring and various servers. The RCS provides functions for automation and remote monitoring control of individual processes at water treatment, water intake, and pressurization plants, while the TMTC provides functions for real-time monitoring and control of water facilities, such as pipelines and drainage basins. The following shows an application example. Tap water is provided through the water intake, receiving, coagulation, flocculation, sedimentation, filtration, purification, transmission processes. The integrated operation system is designed to integrate 2 or more water treatment plants into one center for the efficient operation of water pipelines. The central hub and individual subcenters, water treatment plants, are connected and built using a broadband high-speed communication network, and the monitoring and control scope is divided by region and size and operated on a 24-hour shift basis. In the system configuration, all plants are connected by broadband communication networks, and the monitoring area is divided based on the water supply pipelines and areas. Maintenance for each plant is based on shift work. Let's have a look at the integrated SCADA system. The SCADA system is constructed in an integration center. The standard software is installed for water treatment. It is expected to improve productivity and efficiency for maintenance based on historical data analysis, powerful database, monitoring alarm functions, and accident prevention. Process automation refers to the process of building a program to automate field facilities. For pumps, it refers to automation control for the number of pumps by level and power, while for chemicals, automatic determination of chemical feeding rate based on water quality analysis.
다음은 스카다 시스템의 구성을 간략하게 설명드리겠습니다. 보시는 바와 같이 스카다 서버를 설치하여 안정적으로 운영하도록 이중화로 구성이 되어 있습니다. 스카다 서버는 운영 근무자들이 감시 제어를 할 수 있는 COS, 즉 조작 시스템이 별도로 구성되어 있으며 모든 시스템들은 네트워크로 구성되어 운영되고 있습니다. 이 네트워크는 본부 또는 본사까지 데이터가 모두 전송되도록 구성되어 있습니다. 정수장 군에는 광 케이블을 이용해서 듀얼링 네트워크 구성으로 이중화를 하여 안정적인 네트워크 구성을 하고 있습니다. 또한 스카다 시스템의 가장 필수적인 RCS 시스템은 각 공정별로 설치가 되어 하부 기기인 수위, 유량, 여러 가지 다양한 계측 센서들을 모두 수집하여 이곳에서 자동 제어 알고리즘들이 포함되어 운영을 하도록 구성되어 있습니다. 마지막으로 관로상에 있는 TMTC, 즉 관로상 압력, 유량 등을 원격 감시하기 위해서 분기점에 TMTC 설비들이 구성되어서 이렇게 통신이 되도록 시스템이 구성되어 있습니다. 스카다 시스템에서 HMI에서 제어가 이루어질 경우 RCS PLC 레더에서 데이터가 어떻게 전송이 되고 제어가 되는지 그 로직을 살펴보도록 하겠습니다. 원수 샘플링 펌프 2호기에 대해서 현재 운영 중인 것을 펌프를 꺼보도록 하겠습니다. 이때 보시는 바와 같이 PLC 레더에서는 정지 명령 신호가 활성화되면서 실제 펌프가 정지되는 현상을 보실 수 있습니다. 다음은 펌프를 다시 운전을 하도록 해보겠습니다. 자, 원격에서 신호를 주었고 다시 펌프가 ON이 되는 그 프로그램의 모니터링 상태를 확인하실 수 있습니다. 스카다 시스템의 원격 감시 제어와 관련하여 데이터를 어떻게 표출하고 또 데이터를 어떻게 제어하는지 그 부분에 대하여 시연을 보여드리도록 하겠습니다. 보시는 바와 같이 스카다 서버를 중심으로 RCS가 연결되어 원격에서 감시와 제어를 할 수 있습니다. 지금 보여드리는 예는 RCS 1번, 즉 약품 투입동에 설치되어 있는 원수의 수질을 측정하기 위한 샘플링 펌프를 원격에서 펌프 온, 오프에 대한 시연과 실습을 해보도록 하겠습니다. 보시는 바와 같이 원수에 총 2개 샘플링 펌프가 현재 구성이 되어 있으며 녹색은 정지 상태, 빨간색은 운전 상태를 나타내고 있습니다. 이 표현이 제어가 되었을 때 녹색으로 변경이 될 것입니다. 보시는 바와 같이 제어창에서 리모트로 펌프를 꺼보도록 하겠습니다. 보시는 바와 같이 이번에 펌프가 빨간색에서 녹색으로 변경되었습니다. 다시 한번 펌프를 켜보도록 하겠습니다. 보시는 바와 같이 초록색에서 빨강색으로 변경이 되어 현재 상태를 표시를 하고 있습니다. 수질 연속 자동 측정 기기에 대하여 설명을 드리도록 하겠습니다. 보시는 바와 같이 맑은 물을 생산하여 정수를 내보낼 때 이 수질을 측정하기 위해서 원격에서 샘플링을 하여 이 물을 pH 그리고 잔류염소, 탁도를 측정하여 이 데이터를 스카다 시스템인 RCS에 신호를 전송하게 되고 스카다 HMI에서는 그 데이터를 보고 운영 근무자가 원격으로 감시하여 공정 관리를 하고 있습니다.
For chlorine, it refers to the automatic determination of the chemical feeding rate based on the level of residual chlorine, and for filtration, automation of backwash and filtration. Facilities modernization is the improvement of related automation facilities and systems to efficiently provide the remote control and monitoring functions of the Integrated Operations Center. Systems include a remote monitoring and control system and a video monitoring and control system. Mechanics include valve actuators and chlorine chemical feeding automation systems, and facilities for electricity and motors are included in the category of electricity. The Integrated Operations System is essentially to actively respond to changes in the internal and external environment, such as open markets, regulations by international standardization organizations, fierce domestic, foreign competition, and private companies' entry into the domestic market. The integrated operation can yield results such as labor cost reduction, process standardization, and fast decision-making processes in terms of the efficiency of operations, IT technology-based automation system, and standardized water system application in terms of technology, improvement, and high technology-based competitive edge, and brand advantage in terms of international competitiveness. The integrated operations system is essential to actively respond to changes in the internal and external environment, such as open markets, regulations by international standardization organizations, fierce domestic, foreign competition, and private companies' entry into the domestic market. The integrated operation can yield results such as labor cost reduction, process standardization, and fast decision-making processes in terms of the efficiency of operations, IT technology-based automation system, and standardized water system application in terms of technology improvement, and high technology-based competitive edge, and brand advantage in terms of international competitiveness. The SCADA system can lead to the improvement of water management. In addition, positive results such as risk prevention and efficiency and productivity improvement, stable water supply and optimal use of water resources, and reliable and healthy water supply can be obtained from its introduction and utilization. What is AI? AI stands for Artificial Intelligence. Computer science defines AI research as the study of intelligent agents and as any device that perceives its environment and takes actions to maximize its chances of successfully achieving its goals. Then, what does artificial intelligence mean? No clear definition is given for artificial intelligence, but the common attribute of AI can be expressed as thinking and learning like humans to make decisions. The history of artificial intelligence began in 1956. In the present day, AlphaGo stands as an example of AI. The types of artificial intelligence can be divided into 4 levels from level 1 of simple control program level to level 4 using deep learning. The branches of artificial intelligence can be divided and classified as follows. Major examples of artificial intelligence include AlphaGo. This defeated Lee Se-dol, a professional Go player. Tesla's self-driving car aims to exceed level 4. There have been rapid advances in technologies using artificial intelligence. This artificial intelligence technology follows the subsequent process. The data acquired from the sensor is continuously stored to construct data lakes for big data and follow the process of providing services through data mining, analysis, and algorithms. Artificial intelligence configures the system to make decisions like humans. In the case of automation, the corresponding output comes out according to the given conditions, whereas artificial intelligence finds an unknown black box B through learning from experience. What is the purpose of applying AI to water treatment systems? In relation to autonomous operation in waterworks, the purpose is to autonomously operate all processes, such as water intake, purification, pressurization, distribution, and supply, excluding human decision-making process. The AI system configuration is as follows. Data collection and analysis are done via the interface with the existing legacy systems with focus on the open source-based system, and decision-making targets are provided to the user. New servers are added to configure a new system while utilizing the existing system, and the interface with legacy and storage, analysis, visualization functions are established separately. The Artificial Intelligent Autonomous Operation System has built a visualization system to allow the user to make intuitive judgments. As a result, the coagulant injection rate and raw water classification and condition results can be predicted through monitoring and analysis. In addition, the artificial intelligence system visualizes the results of the step-by-step analysis with explainable AI, XAI, and provides the visualized results. Artificial intelligence is implemented so that it can analyze and monitor the performance of the server and software in real time. A prediction algorithm is built based on the coagulant injection ratio, and a simulation function is provided to users. R2 values for each type of coagulants were compared to verify the prediction accuracy of the artificial intelligence system in relation to the operation based on the worker's experience in the past. Two types of coagulants, APAC and Polymax, were compared, and the R2 values of each were compared for training groups and test groups, respectively. In terms of water quality stability, a comparison between the AI values and the results of a total of 6 jar tests confirmed that the prediction results were very accurate at 1 to 3 ppm. Even in terms of the adequacy of chemical injection rate for the settled water turbidity operation, the coagulation efficiency was excellent, which confirms that the settled water turbidity was further improved compared to that of the existing operation method. This in turn suggests that it is very effective at reducing the amount of the coagulant, as the settled water turbidity was reduced by up to 1.08 NTU compared to that of the same period in the past. Regarding chemical coagulant reduction effects, it was confirmed that the use of chemicals was reduced by 4.17% compared to the previous operation data, 6 months, and increased by 1.03% compared to the current operation data, 14 days. Therefore, it is expected to reduce the cost of coagulant by about $560 million per year when expanded to all business sites. An AI-based future water treatment plant is defined as a smart water treatment plant.
다음은 화성권 지사의 AI 시스템을 간략하게 설명하도록 하겠습니다. 이 AI 시스템은 전 세계적으로 물 산업계에서 최신 기술 트렌드를 적용한 최초의 사업장이라 자부할 수 있습니다. 주요 세부 화면을 살펴보도록 하겠습니다. 8당에서 정수장까지 들어오는 원수의 수질을 실시간으로 측정하여 이 데이터를 분석해서 해당 알고리즘에 따른 주요 약품 종류와 약품 주입률을 예측하고 그 예측값을 저희 스카다 시스템에 전송하여 실시간으로 자동 제어하도록 구성되어 있습니다. AI 시스템의 가장 큰 특징은 이 약품에 대한 시뮬레이터 기능으로서 원수 수질의 조건을 입력하게 되면 최적의 약품 종류와 약품 주입률을 예측하는 것이 가장 큰 특징이라 할 수 있겠습니다. 과거에는 운영 근무자들의 경험적인 판단에 의해 약품 종류와 약품 주입률을 결정하였으나 지금은 체계적이고 과학적인 데이터를 기반으로 한 AI 시스템에 의해서 최적의 약품 공정이 이루어지게 만들어주고 있습니다.
The future waterworks system is equipped with the autonomous operation system of water treatment plant, smart EMS, predictive maintenance system, and intelligent video monitoring system. Based on the establishment of AI and big data-based autonomous operation system, the smart water treatment plant seeks to reduce human errors and improve operational efficiency for stable tap water production. Looking at the functions of each system, the autonomous operation of water treatment plants means the operation of autonomous water treatment plants in which artificial intelligence, big data-based analysis prediction is available. And the smart EMS is a system to measure and diagnose real-time power consumption for the optimal management of power use by process. The predictive maintenance of facilities is a work environment where preventative maintenance of water treatment-related facilities is possible through big data-based analytical prediction. And the intelligent video surveillance is a system to provide a safe management work environment based on the real-time monitoring and analysis using intelligent video technologies. The objectives of the future waterworks system are to lay a foundation for autonomous operation through the development of algorithms that enable autonomous operation for each process and improvement of related facilities for the entire water treatment process, and to develop a standard model for smart water treatment plants through the development of element technology to enable predictive maintenance, safety management, and energy management on an autonomous operation platform. The standard model is designed to establish the technology level related to the standards required for the installation of AI platforms, performance evaluation tools for each function, related facilities, servers, measurement equipment, and control standards.